Introduction. Divya, today I will show you how to make a soft bread.
Mother, I would love to see that.
First of all, we take a bowl and put all the ingredients into it to make a paste. Now we add yeast in the mixture and keep it for some time. Then it will be ready for baking. Now our bread is ready to serve.
Ah, it's looking quite good. Mother, can I ask you something?
Yeah, sure.
Why did you add yeast in the mixture?
Okay, I will tell you. Yeast acts as a catalyst in the process of fermentation required in the making of bread. Yeast reacts with sugar in flour and produces carbon dioxide in the process. Carbon dioxide fills thousands of bubbles in the dough. When the bread has baked, then it becomes fluffy and soft.
Okay, Mother. I got the answer of my question and I wanted to know something more about this.
To know more about this, you have to study about the chemical kinetics. So, students, today we'll discuss more about the chemical kinetics. Objectives. At the end of this lesson, you will be able to define chemical kinetics, classify chemical reactions, describe rate of a chemical reaction, calculate average and instantaneous rate of reaction, know about the factors affecting the rate of reaction, analyze order of reaction, calculate molecularity of a reaction, calculate half-life of a reaction, understand effect of temperature and catalyst on the rate of the reaction, derive Arrhenius equation, explain collision theory. Definition. Chemical kinetics is the branch of physical chemistry which deals with the study of the rate of chemical reaction and the mechanism by which the reactions occur. There are three important aspects of the study of chemical reactions. Will the chemical reaction be feasible? If the reaction is feasible, how far will it proceed? How fast a reaction would occur? Types of chemical reactions. Various reactions can be categorized into three types depending upon the reaction rates. Very fast reactions. This type consists of reactions which occur almost instantaneously. The rates of such reactions cannot be determined easily. For example, the precipitation of AgCl occurs instantaneously by addition of aqueous solution of sodium chloride to aqueous solution of silver nitrate. Very slow reactions. This type comprises reactions which occur at a very slow rate. The rates of such reactions are hardly of any physical importance. These reactions may require months or even years together for their completion. For example, rusting of iron. Moderately slow reactions. This type consists of reactions in between the very fast and very slow reactions. These reactions proceed at a moderate speed which can be easily measured. For example, hydrolysis of starch. Rate of a chemical reaction. The rate of a chemical reaction is the speed or velocity with which a reaction takes place. It is defined as the change in concentration in any one of the reactants or products per unit time. It can be expressed by two ways. Qualitative rate. It is based on certain visual parameters like disappearance of reactants, color change, effervescence, etc. The rate expressed as such provides arbitrary conclusions about the rate of a reaction. Quantitative rate. It provides much better information about the rate data and the accurate rate of a chemical reaction. Quantitative rate may be expressed by two ways. The rate of decrease in concentration of any one of the reactants, the rate of increase in concentration of any one of the product. Units of rate of reaction. The concentration of substance is expressed in mole per liter and the time is expressed in seconds or minutes or hour. Hence, the units for reaction rate are moles per liter, per second, or moles per liter per minute, or moles per liter per hour. For gaseous reactions, the concentrations of reactants and products are given in terms of partial pressures, and pressure is expressed in atmospheres. Hence, the units of rate of reaction will be atom per second, or atom per minute, or atom per hour. Average rate of reaction. It is the change in concentration during a finite interval of time. In order to find the rate of reaction, the concentration of either a reactant or a product is determined at different intervals of time. Some observable property like volume, pressure, optical rotation, pH, and electrical conductance, which is related to concentration, can also be used to follow the progress of the reaction. It is directly measured at different time intervals without withdrawing the reaction mixture. Average rate is equal to negative delta C upon delta T. Instantaneous rate of reaction. It is the change in concentration of either reactant or product per unit time at a particular instant of time. To express instantaneous rate of reaction, we choose a small interval of time at that particular instant of time during which the rate of reaction is supposed to remain constant. If dx be the small change in concentration during small interval of time dt, then instantaneous rate at that instant is given by dx by dt. For a reaction in which A tends to B, instantaneous rate is equal to dB by dt. Rate expression and stoichiometry of the reaction. Individual rate expressions in terms of various species of a chemical reaction are called relative rates. Relative rates are made equivalent by dividing the rate expression by stoichiometric coefficient of the species in the balanced chemical equation. For a reaction, small a, capital A, plus small b, capital B, makes small c, capital C, plus small d, capital D. The rate of a reaction can be expressed as Example on rate expression and stoichiometry of the reaction. Let us consider the following reaction. H2 plus I2 gives rise to 2HI. The rate of reaction can be expressed in the following ways. Minus d by dt of H2 or minus d by dt of I2 or plus d by dt of HI. The reactants and product have different stoichiometric coefficients. It means that as 1 mole of either H2 or I2 disappears, 2 mole of HI are formed. The rate of appearance of HI is twice the rate of disappearance of H2 or I2. Thus, minus d by dt of H2 is equal to plus 1 by 2 d by dt of HI. Similarly, minus d by dt of I2 is equal to plus 1 by 2 d by dt of HI. Therefore, minus d by dt of H2 is equal to minus d by dt of I2 is equal to plus 1 by 2 d by dt of HI. Factors affecting the rate of a reaction. Effect of the nature of reactants and products. A chemical reaction involves breaking of bonds in the reactants and formation of new bonds in the products. The number and nature of the bonds to be broken and formed will be different in different chemical reactions. Effect of concentration. Higher the concentration of the reactants, faster is the reaction. As the reactants are consumed in the reaction, the rate of reaction decreases with the progress of reaction. Surface area. As we subdivide a substance, its surface area increases. Therefore, smaller the particle size, greater is the surface area, and therefore faster is the reaction. Presence of a catalyst. A catalyst generally increases the rate of a reaction without itself being consumed in the reaction. Temperature. The rate of a reaction increases with an increase in temperature. Generally, the rate of a reaction doubles for every 10 Kelvin rise in temperature. Presence of radiation. Some reactions do not proceed in dark but take place in the presence of light, known as photochemical reaction. Effect of concentration. When a chemical reaction occurs, the reactants change over to products. With the passage of time, the concentrations of reactants decrease while those of products increase. Law of mass action. At a given temperature, the rate of a chemical reaction is directly proportional to the product of molar concentrations of reacting species, with each concentration term raised to the power equal to numerical coefficient of that species in the chemical equation. For the given reaction, rate of a reaction is equal to the product of K, A raised to the power A, and B raised to the power B. If the concentration of all reacting species is taken as unity, then rate is equal to K. Hence, rate constant is defined as the rate of a reaction when the concentration of each reactant is taken as unity. Rate of reaction versus rate constant. The important differences between the rate of the reaction and rate constant of the reaction are: rate of reaction depends upon the concentration of reactant species at that moment of time, while rate constant refers to the rate of reaction at the specific point when concentration of every reacting species is unity. Rate of reaction is the speed at which the reactants are converted into the products at any moment of time, while rate constant of a reaction is constant of proportionality in the rate law expression. Rate of a reaction generally decreases with the progress of reaction, whereas rate constant of a reaction is constant and does not depend on the progress of the reaction. Order of reaction. It is defined as the sum of powers or exponents to which the concentration terms are raised in the rate law expression. The rate law expression for a given reaction is given by: rate of reaction is equal to product of K, A raised to the power M and B raised to the power N. The order of this reaction is equal to M plus N. Order of the reaction with respect to A is M and with respect to B is N. If the sum of the power is equal to 1, the reaction is called first-order reaction. If the sum of the powers is 2 or 3, the reaction is second-order or third-order reaction respectively. The order of a reaction can also be 0 or fractional. Units of rate constant for different orders. Zero-order reaction. Rate is equal to dx by dt, which equals to the product of k and a raised to the power 0. Thus, units of rate constant for zero-order reaction are mole per liter per second. First-order reaction. Rate is equal to dx by dt, which is equal to the product of k and a raise. Thus, the unit of rate constant for first-order reaction is per second. Second-order reaction. Rate is equal to dx by dt, which is equal to the product of k and a raised to the power 2. Thus, the units of rate constant for second-order reaction are liter per mole per second. Third-order reaction. Rate is equal to dx by dt, which is equal to the product of k and a raised to the power 3. Thus, the units of rate constant for third-order reaction are liter square per mole square per second. Molecularity of a reaction. The number of reacting species which must collide simultaneously in order to bring about the chemical reaction is called the molecularity of the reaction. When one molecule is participating in simultaneous collision, the reaction is unimolecular. When two molecules are participating in simultaneous collision, the reaction is bimolecular. When three molecules are participating in simultaneous collision, the reaction is trimolecular. Molecularity of a reaction is always a whole number. Order of reaction versus molecularity of reaction. The important differences between the order of reaction and molecularity of the reaction are: order of reaction is the sum of the powers of the concentration terms in the rate law equation, whereas molecularity of reaction is the number of reactant species that must collide simultaneously so as to result in a chemical reaction. Order of reaction can be a whole number or fractional and even 0, whereas molecularity of a reaction is always a whole number. Order of reaction has to be determined experimentally, whereas molecularity of a reaction is calculated for each elementary step by adding number of reacting species. It is a theoretical concept. Zero-order reaction. A reaction is zero-order if its rate is independent of the concentration of reactants. For a zero-order reaction, A is changing into products. If initial concentration of reactants is A, naught, and concentration after time T is A, then the rate of reaction is given by minus dA by dt is equal to product of K and A raised to the power 0, which is equal to K. It can be written as dA is equal to minus K dt. Integrating both sides, we get A is equal to minus KT plus C. At T is equal to 0, A within parentheses is equal to A naught. Therefore, C is equal to A naught. By putting the values in the equation, we get A is equal to minus KT plus A naught. Or it can be written as K is equal to 1 upon T multiplied by A naught minus A. First-order reaction. Let us consider a first-order reaction in which A is changing into products. if the initial concentration of reactants is A, naught, and concentration after time T is A, then the rate of the reaction is given by minus dA by dt is equal to product of K and A. It can be written as minus dA upon A is equal to K dt. On integrating both sides, we get minus natural log of A is equal to Kt plus constant. Put the value of T is equal to 0 in the above equation, and we get constant is equal to minus natural log of A naught. Now put the value in the above equation, and we get minus natural log of A is equal to Kt minus natural log of A naught. Changing into common log, we get Kt is equal to 2.303 log A naught upon A. It can be written as K is equal to 2.303 upon T multiplied by log A naught upon A. Half-life of a reaction. Half-life of a reaction is defined as the time during which the concentration of the reactants is reduced to half of the initial concentration. It may also be defined as the time required for the completion of half of the reaction. It is denoted by T half. Half-life for zero-order reaction. The integrated equation for the zero-order reaction is A is equal to A naught minus Kt. At time T half, A is equal to A naught by 2, or A naught by 2 is equal to A naught minus Kt, or Kt half is equal to A naught by 2. It can be written as T half is equal to A naught divided by 2K. Hence, the half-life of a zero-order reaction is directly proportional to the initial concentration. Half-life for first-order reaction. We know that for the first-order reaction, K is equal to 2.303 upon T multiplied by log A naught upon A. T can be calculated from this equation as T is equal to 2.303 upon K multiplied by log A naught upon A. At T half, A is equal to A naught divided by 2. T half is equal to 2.303 divided by K multiplied by log 2. It can be written as T half is equal to 0.693 divided by K. Hence, the half-life period for first-order reaction does not depend upon initial concentration of the reactants. For the reaction of nth order, T half is inversely proportional to 1 upon A naught raised to the power n minus 1. Pseudo-first-order reaction. There are circumstances where a second-order reaction might appear in an experiment to be first-order is called a pseudo-first-order reaction. That is, when one of the reactants in the rate equation is present in great excess over the other in the reaction mixture. For example, the inversion of cane sugar is a bimolecular reaction, but it is a first-order reaction as concentration of H2O is quite large and does not change appreciably. Temperature dependence of the rate of a reaction. For homogeneous reaction, the rate of reaction approximately doubles for every 10-degree rise of temperature. The ratio of rate constants of a reaction at two temperatures differing by 10 degrees is known as temperature coefficient of the reaction. Value of temperature coefficient for most of the reaction is close to 2 and in some cases it approaches to 3. When the temperature is increased by T plus 10 degree, the curve flattens. Now the shaded area ABEF represents fraction of molecules having greater energy than threshold energy. The area ABEF is more than double the area ABCD. The fraction of the molecules possessing equal energy to or greater than threshold energy becomes almost more than double. Hence, the rate of the reaction also doubles for every 10 degrees rise in temperature. Thus, increase in the rate of reaction with increase in temperature is due to an increase in the fraction of molecules having energy in excess of threshold energy. Effective collisions and threshold energy. Collision frequency. It is defined as total number of collisions per unit volume per unit time. Effective collisions. Collisions which lead to the formation of product molecules are called effective collisions. Rate of reaction is equal to F multiplied by Z, where Z is the collision frequency and F is the fraction of collisions which are effective. Threshold energy. The minimum energy that the reacting molecules must possess in order to undergo effective collisions to form the product is called threshold energy. Activation energy and activated complex. Activation energy. It is the difference between the threshold energy and the average kinetic energy possessed by the reacting molecules. Activated complex. It is defined as intermediate formed between reacting molecules which is highly unstable and readily decomposes to yield product. Characteristics of an activated complex. The potential energy of the activated complex is maximum. The energy required to form activated complex is called activation energy. The activated complex has a transient existence and breaks up at a definite rate to form the products. Arrhenius equation. Arrhenius equation relates rate constant with temperature as K is equal to the product of A and e raised to the power minus EA upon RT, where A is the frequency factor and EA is the activation energy. Taking natural log on both sides, we get natural log K is equal to natural log A minus EA upon RT. Changing natural log into common log, we get log K is equal to log A minus EA upon 2.303 RT. If K1 and K2 are the rate constants at two temperatures T1 and T2, we have log K1 is equal to log A minus EA upon 2.303 RT1. Log K2 is equal to log A minus EA upon 2.303 RT2. On subtracting the above two equations, we get log K2 upon K1 is equal to EA upon 2.303 R multiplied by T2 minus T1 upon T1 T2. Effect of catalyst on the rate of the reaction. Catalyst is a substance that increases the rate of a chemical reaction without itself suffering any permanent chemical change. It participates in a chemical reaction by forming temporary bonds with the reactants, resulting in an intermediate complex. It provides an alternate pathway or reaction mechanism by reducing the activation energy between reactants and products, hence lowering the potential energy barrier. It doesn't change the equilibrium constant, but only helps in attaining equilibrium faster. A small amount of the catalyst can catalyze a large amount of reactants. Collision theory of chemical reactions. Only effective collisions bring about a chemical reaction. The collisions in which molecules collide with sufficient kinetic energy and proper orientation so as to facilitate breaking of bonds between reacting species and formation of new bonds to form products are called as effective collisions. Activation energy and proper orientation of the molecules together determine the criteria of an effective collision and hence the rate of chemical reaction. Rate is equal to product of P ZAB and e raised to the power minus EA upon RT, where ZAB is equal to collision frequency of reactants A and B. P is equal to probability factor, and e raised to the power minus EA upon RT is equal to fraction of molecules with energies equal to greater than EA. Did you know? In 1864, Peter Waugh and Cato Gullberg pioneered the development of chemical kinetics by formulating law of mass action. The rate of a chemical reaction depends on the medium in which the reaction occurs, whether a medium is aqueous or organic, polar or non-polar, or liquid, solid, or gaseous. The kinetic isotope effect is the difference in the rate of a chemical reaction when an atom in one of the reactants is replaced by one of its isotopes. Half reactions are two reactions created by breaking down a complex reaction into simpler parts. Summary. Let us summarize what we have learned. Chemical kinetics is the branch of physical chemistry which deals with the study of the rate of chemical reaction and the mechanism by which the reaction occurs. Rate of a chemical reaction is defined as the change in concentration in any one of the reactants or products per unit time. Instantaneous rate of reaction is the change in concentration of either reactant or product per unit time at a particular instant of time. At a given temperature, the rate of a chemical reaction is directly proportional to the product of molar concentrations of reacting species, with each concentration term raised to the power equal to numerical coefficient of that species in the chemical equation. Order of reaction is the sum of powers or exponents to which the concentration terms are raised in the rate law expression. The number of reacting species which must collide simultaneously in order to bring about the chemical reaction is called molecularity of the reaction. Activated complex is the intermediate formed between reacting molecules which is highly unstable and readily decomposes to yield product. Half-life of a reaction is defined as the time during which the concentration of the reactants is reduced to half of the initial concentration.